This is TechDays.
Good morning. Thanks a lot for making it in so early after the party. Congratulations for being here at 9 a.m. I appreciate it. I want to first open up with sort of a normal day in the life for us. So what this shows you here is just an average day in the middle of May this year when 2.6 million people in 232 countries around the world were attacked with 1.7 new malware attacks that we had never seen before. Totally new, 1.7 million on a single day. What's worse is that 60% of those first seen attacks, they were over within the hour. So in the security industry, we like to think a lot about response, security response. How are we going to respond to an attack? Well, when you've got an hour or less, and you've got 1.7 million new things that you have to deal with in a single day, there's no response time that matters. You either get it right from the start, or you failed. We've got 500 million people counting on us every single day to get this right, to block this stuff the second that we see it. And we've got lots of attackers out there who want to ransom your systems. They want to steal your credentials. They want to get the banking credentials of consumers, right? They are working hard. 1.7 new things every single day. So this is the stuff that keeps us up at night, right? And being able to predict and be able to stop these threats, it's absolutely critical. So we're investing, right? Microsoft is spending a lot of money to try to protect you. We've got thousands of full-time security professionals at Microsoft. We're spending over $1 billion US dollars every single year in security. Every day we're processing trillions of signals, and we're finding 5 billion new threats every single month. So I think it's safe to say that when it comes to security at Microsoft, we're all in, right? We are investing to try to stop this from happening. But we know that this has to be easy for you, right? Security is not going to work if it's complicated. We know it's not going to work if there's a heavy burden on your end users, if they're bombarded by security alerts every day. They don't know what to do, right? This has to be low cost on the client. That's why we're doing things like building in the security, not bolting it on. That's why we have such a high focus on performance. Low performance, high effective protection at the client. That's why we're investing in security admin tools and security response tools for the professionals that need it, because we know that you need a console where you can see everything that's going on, where you can respond, where you can put in your automatic remediation things for when things do go wrong, right? We're investing to help you. So that's enough about the overall product stuff. Let me tell you a little bit about me and why I'm here talking to you today. So I work for the research team, the Windows Defender Advanced Threat Protection Research Team. And my team in particular focuses on using machine learning to predict threats. So that day in the life that I was telling you about, where we see 1.7 million new things every single day, that's what keeps my team up at night, because we are accountable for predicting that it's a threat and blocking it at first sight. And I'm really honored to be here today, to be here in Sweden. I love visiting this country. Really honored to be here to tell you a little about how that works and kind of demystify this whole, machine learning thing, right? Because I think for a lot of folks, it's sort of black magic. Is it really real? Today, I hope that by the end of this session, you'll believe that it's real and you'll understand the value of it. So I do want to start off with a little bit of demystification, and I'll start with terminology. What is it? Is it AI? Is it machine learning? I don't know. We use them interchangeably today. The term artificial intelligence, some will argue, actually started back in the antiquities, back with the great philosophers, when they thought that it might be possible to take something synthetic and make it seem human. But the real research actually started in the 1950s, the real research behind artificial intelligence, and in 1959, the term machine learning was born. Now, artificial intelligence was really focused on trying to make something appear to be human, something appear to act human. But machine learning actually took that one step further. So the idea behind machine learning is that you teach a machine to be smarter than a human. But it didn't really have the kind of gravitas that it has today, didn't really have the effect that they wanted it to have back in the 1950s because they didn't have the data, they didn't have the compute power, right? It was really just a dream. And then in the 80s, fun decade, great decade, in the 80s, still didn't have the compute power, still didn't really have the algorithms right. We turned to something called expert systems. So in the 80s, neither of these terms were really very cool. We looked at expert systems, which is basically an automated way of telling a machine to sort of act like a human again. But today, what's old is new again, and AI and ML you'll hear used interchangeably. But I'm a little old school myself, so we really focus on using machine learning for the classic definition, which is to train a machine to be smarter than a human. So there's two basic types of machine learning, and it's pretty easy to separate them out in terms of labels. So a label is a name that you apply to something that goes into your machine learning model that tells you what that item is. And for our purposes, we focus on something that is malicious and something that is not malicious or something that is clean. So the big difference between supervised learning and unsupervised learning is that supervised uses those expert labels. So the expert labels feed into the machine learning algorithm. The machine learning algorithm learns from those labels and learns from the properties of the files or samples that go into that machine learning system. And then it predicts what whether something is malicious or clean on brand new samples that it has not seen before. Unsupervised learning, on the other hand, doesn't need those labels. Unsupervised learning is really good at removing human bias. And we all have it, right? Security researchers are no exception. You have to develop bias to become an adult. Otherwise, your brain just won't function. Unfortunately, this causes blind spots, right? If you think you know the answer, then you're going to miss something. And the beautiful thing about machines is that they don't have to have these biases unless you teach it to them. So the really nice thing about unsupervised learning is that it can provide a great complement to your supervised models by uncovering those biases. For example, there are clustering algorithms that will group like things together without having any kind of predisposed labels. It's really good at finding the unknown unknowns, right? Pockets of things that have yet to be discovered by a researcher. It's also good at finding similar malware families that maybe a researcher didn't know about yet. So it's a fantastic complement to a supervised approach. Another way to use unsupervised learning is through anomaly detection. And this is simply the machine learns what's normal, and then when something that is outside of that norm occurs, it doesn't label it good or bad, but still it's a great complement to pull into a supervised approach to find some things that perhaps a normal researcher wouldn't find. Supervised learning is really the primary method we use for malware prediction, however. And it's a fantastic way to scale researcher expertise. So if you think about what a human can hold in their brain, right? It's about 7 digits. I think that's the industry or the average of what a person can hold in your brain. Like 7 different variables at the same time. So a machine, the capacity is infinite, right? So when a malware researcher looks at a piece of malware and they find maybe 5 attributes that make it malware and they label it as malware, that file actually has hundreds of thousands of other attributes that they just simply can't take the time to go figure out. Well, the machine can. So when the researcher labels that file and those hundreds of thousands of attributes go into the machine learning algorithm, then the machine can say, oh, actually, it's this set of 1,000 that make this thing malware. And I can use that to predict new malware that maybe the researcher wouldn't have predicted. Their simple 7-component algorithm was too simple to find. And that's how you can take one single thing that a malware researcher has labeled and turn that into a prediction for tens of thousands, for hundreds of thousands. It's a fantastic thing to scale. So we'll talk a little bit about machine learning, how we build machine learning for the Windows Defender ATP product. It starts with having a really great set of labeled samples. And this is critical. So you may have seen people take samples from VirusTotal, build machine learning algorithms that can then predict new malware samples. But where's the clean files? If you don't have a really curated set of clean and malware in your training set, your machine learning algorithm will never work in the real world. So this is a critical piece of the development process for us, is making sure that our sample set is indicative of the real world and of what our customers see day to day. Feature selection is another critical piece. So we have machines automatically select features for us because sometimes the machines can find them faster than researchers. And we also have researchers who specify certain things that they know are indicative of malware. And all of these features go into the machine learning model for training. So then comes the experimentation part. This is where you try out different learners. Maybe you want to try a deep learning model, because this is a back-end cloud-based system. You've got infinite compute power. Your deep learning model, although it's super intense, you can run it. Or maybe you're developing this for a client, but the client needs to be super performant. So you're going to look at a different type of learner, something that's fast, something that won't have a lot of impact on the endpoint. And then you want to look at the parameters of these learners, because that can change the outcome as well. So a lot of work goes into this experimentation phase for us. Then when we feel like we've got a good product, we ship. And we ship, but it's not on by default, so it's not blocking. With the ATP product, we can ship this to the cloud or the client in non-blocking mode to make sure that it's really performing the way that we saw in our experimentation phase. Sometimes it takes us a couple of weeks. Sometimes it takes us a month. We do a little more tweaking and tuning. And when we see that we've got it right and that this is going to be good for customers, we turn it on. This gives you an idea of the data that goes into these models. And it's pretty intense. So we're looking at static attributes of files and, the normal stuff that you might expect. We're looking at partial hashes. We're looking at who signed the file. Is the file signed? But we also look at behavioral components. Was this related to another file? Was this injected from another file? Was this downloaded from somewhere? What are the contextual elements related to this entity that make it more relevant to malware or more like a clean file? All of these components are important. And take something like the URL, which can be one static property, but a machine can actually turn that into components. So we can do things like n-grams, where you take 3 characters that are in a row, or skipgrams, and those become features in models. So you can see how these thousands of features can turn into tens of thousands of features, hundreds of thousands of features, and in some of our models, millions of features. Now I'm going to make a joke, okay? So have you heard the phrase, there's an app for that? Anybody? Yes? Okay, there's an app for that. Okay, I'm going to start saying there's a model for that, because there is. All right. Is it new malware? Is it old malware? There's a model for that. Different models. Okay? Yes, there is a model for those. What about program files? How about JavaScript? What about Java? VBS? There's a model for that. Yeah, for every single one of them. All right, so what about my enterprise? It's not like what you see at the consumer level. It's different malware, different clean files. Okay, there's different models for that. All right, so, these static file properties, it's different from this behavioral stuff. Like, surely your model doesn't, work on both of those. Actually, no, yeah, they're different models. We've got a model for behavioral. We have a model for static file properties. There's a model for that. There's lots of different models, okay? And the diversity doesn't just extend to what we're trying to target. It actually extends into the learners and the numbers of features that go into those models. So for example, for something that might have millions of features, and we use a deep neural network to predict whether something is malware, that's a great cloud model, right? Because it's, takes a lot of time to run, takes some time to analyze, not something you'd want to do on the client necessarily, something that's super performant in cloud. Versus a client-based model where maybe you just have 30 features or a few hundred features, and you've got a linear model, which is super small because you don't want to send a big, huge update down to your client, and super fast, right? So we have a large diversity of models to serve multiple purposes. And you might think, man, that sounds really inefficient. Why do you have so many different models? Why can't you just have the perfect singular model that does it all? Well, turns out that's a vulnerability. There have been a lot of research published on how it's very easy to exploit and tamper with a big singular model, all right? So we actually did a talk at Black Hat this year to discuss this. It turns out that diversity, just like diversity is critical to our businesses, it's critical for our society, diversity is also critical for machine learning. And if you're interested in this topic, it's a 1-hour discussion. The presentation is uploaded to Black Hat, and you can go have a look at it and see the research that we have done, the real attacks we have seen in the wild on our models, and the red team exploits that we performed to see how we could make our model stronger. It turns out that diversity is really key to having a tamper-resilient machine learning system. Right? So we'll talk a little bit about where within the Windows Defender ATP product this machine learning is incorporated, and it's in multiple layers. So this funnel here shows malware and clean files that are trying to get through, right? The orange dots are the malware. So most of our protection comes at the client level. We have local machine learning that runs there. We have heuristics. We have behavioral detection that helps protect right at the client without ever having to talk to our cloud. And of course, this protection happens instantly. If you don't have an answer at the client, let's say the client thinks that this is suspicious, but it's not really sure, it will send all of that metadata that you saw in a small blob up to the cloud for analysis. And the cloud, through these metadata-based machine learning model rules, will return a response within milliseconds about whether it thinks that what the client saw was malicious or not. So this happens in milliseconds. This is instantaneous. This is real-time protection still. If those metadata-based models don't know the answer, we might request a sample of the activity that the client saw. And the reason why we do this is because there's some additional feature extraction capabilities that we have at the cloud that wouldn't necessarily be performant to do on the client, right? Again, we're thinking about the end user. We don't want to bog them down with something that's hogging up all their resources. So we're going to grab that sample, send it up to cloud, do a quick extraction of additional features, and run a deep learning model against it to figure out whether it's clean or malicious. This happens within seconds, and this is a communication between the client and cloud. The cloud says, you know, I think that thing's suspicious, just hold for a couple of seconds. The client says, gotcha, I'll wait. Waits a couple of seconds, and once the cloud has extracted those properties, run the deep learning models, sends the response back, the client knows whether it can let that file run or whether it needs to go quarantine that file because it's bad. There we go. The last two are a little slower. So the first ones that I talked about, these are all real-time protection capabilities. The last few are a little slower. So this first one is called detonation. And with detonation, you actually run that malware within a virtual machine. You know, some malware will evade this. It doesn't work for everything, but we do some additional feature extraction there. We run that data back through our machine learning models. It helps strengthen them, and sometimes it does result with a protection response within a couple of minutes and adds another layer of defense. With big data, this is analysis that sometimes processes over days. It uses signals from across the company. Sometimes it takes just a couple of hours, but it's a little slower. It doesn't provide real-time protection, but again, provides one more layer down the chain. So, what if your clients can't talk to the cloud? It's okay. It's okay. We're still going to take care of them, okay? We have some answers for you. It's not the end of the world, all right? So let's say the protection stops at the client. Well, even with cloud-connected clients, 75% of the protection for them still happens at the client. And the vast majority of that protection happens pre-execution. So even when you're talking to cloud, we're stopping it in real time, right? We're not necessarily waiting on the behavioral characteristics to kick in. So at the client, you're going to have local machine learning models, you're going to have heuristics, and for persistent threats, for things that some threats do stay around for a couple of days, sometimes they stay around for weeks or months, we will send down protection to the client because, you know, if you don't have to make a cloud call to block a threat, why do it? So we'll ship some protection down to the client so that it can block it when it sees it. So all of these things still exist, right? Now, the thing that you may see if that client is not cloud connected is more behavioral detection kicking in. So let's say that threat goes through, you know, the regular local heuristics, local machine learning protection, and we don't have an answer and we can't talk to cloud. That file may run. When something runs, it needs to do bad things. Or even if it's fileless, it may need to do some process injection. To do something bad on the system, the malware has to do something. Even if it's fileless, there will be a behavioral signal there. So for these clients that don't have cloud connectivity, you may see more behavior-based detections on them. But there's some other mitigations that you can consider. We have a really large number of attack surface reduction rules, things that lock out exploit vectors, make it really hard for attackers to abuse Microsoft Office documents, PDF documents. There's USB controls. There's all types of mitigations that you can deploy through attack surface reduction rules. And for your disconnected environments, you may want to consider that. In fact, if any of you are thinking about disconnected environments or you've got clients that are intermittently disconnected, I would love to talk to you after this because I'm doing some research on the threat models for those different types of scenarios. So please find me sometime today. I'll be at the booth. I'd love to talk to you more about that. So in addition to the attack surface reduction rules, you can also think about application control if that makes sense for that client. So that was a lot of philosophical stuff, a lot of product detail. I want to walk you through some real-world examples of how machine learning helped keep our customers safe. So this first one is your payment was declined. All right? Most of these things are using some type of social engineering lure to get people to open up that document or install that file. So this one was, your payment was declined. And in this case, there was only one victim. This victim was in the UK. This is one of these examples where we only saw one instance of this particular attack. Started out as an email, and that email had a link to a malicious document. That malicious document was hosted on a good website, so it wasn't a website that could be blocked, right? It's just the document was malicious. It had a macro inside it, and when that macro runs, it connects to a website and downloads the actual payload of the attack, which would do something malicious to that person if they had been infected. So what did we do? How did ATP decline? Your payment was declined. This is what we did to protect the system. So at the client, we did a quick extraction of dynamic and static properties, and we sent all of those details to the local machine learning model that was on that client. And in this case, these signals, they were enough. Local machine learning model said, yeah, that's malware, you need to block that, and sent that information to the client, and the client blocked it within milliseconds. Person was protected. No cloud call required. This next example was a very large-scale attack. It affected mostly Russia, Ukraine, and Turkey, but the impact was pretty big. And the impact wasn't just on the folks who got, who encountered the malware, but it was also big on the company whose reputation was damaged because this happened. So the company in question is called MediaGet, and MediaGet, it's a consumer-focused company. They create torrent software, and to be honest, they're what we call potentially unwanted software. So if you are a commercial customer and you have chosen to use the block potentially unwanted software option, you wouldn't have had any of this torrent software in your network. But for most consumers, they don't use this feature. It's an enterprise feature. So for consumers, they may have had this torrent software. In fact, many of our consumer folks did. And what happened here is that these attackers infiltrated this company, and they were able to send a tampered copy of their software down to all of their clients. So it was essentially a fake version of the MediaGet torrent software. And they sent down this malicious version of the software to all the clients. They didn't do anything at the time. But what they did is they added this unusual persistence mechanism. So a feature to make it really hard to uninstall or get that software application off of the box. And from our behavior monitoring capabilities, we know that this is a technique that's often used by malware. So this was our first flag that something was going wrong here. But still, they weren't doing anything, right? So they put in the persistence capability and waited. Well, then they started downloading coin miners. Now, this was their end game, right? To get all these systems infected and then download coin miners and make a fast buck. So what did we do to stop this attack? How did we foil? Foil. These aren't funny. Okay, this must be some translation thing here. Okay, again, we extracted dynamic and static properties, and for us, it was the malicious behavior that tipped us off. This kicked off a query to our cloud. We sent all of that metadata to our cloud, and we had multiple machine learning models flag this as malware, clear as day. And within milliseconds, we sent that response back to all the clients that had received this bad update. And the clients were instructed, block this malware, don't let it run again. There's a ton of blogs on this if you're interested. Supply chain attacks were a big thing this past year, so lots of details if you want to go find out more. This next example is another really small one. And this was a malware family called Sniff. It was highly targeted, mostly focused in the US. And again, it used a malicious document to try to trick people into opening it. It came attached to an email. And the malicious document, when you open it, it says, oh, you need to enable these additional word features, which enabled the macro to run. Once the macro runs, it kicked off this heavily obfuscated PowerShell script. And that PowerShell script would go download Sniff, which was a password and information stealer. So something that's trying to get the credentials of the person who's on that machine, any login, banking information that they may have. These folks were off after all kinds of information. The particular lures that they used were highly differentiated. So these attackers knew the location of their targets. And they knew the local businesses that supplied those targets. So, for example, in Nebraska, in the documents that they sent to those victims, they used DMS, which is the name of a local landscaping company. In St. Louis, Missouri, they used Dolan Care. This was an assisted living facility for elderly people, right? That was in the St. Louis area. Then in Johnson City, Tennessee, they used Dockery, which was a floor covering company. And these are just 3 examples. There were like 20 different business names that they used to try to trick these people in these localized areas into thinking that it's a supplier sending them information that they need to open and, act on. Really tricky social engineering. So who were the targets here? There were consumers, definitely some consumers that received these emails. Lots of local, small commercial businesses. But they didn't stop there. This hit universities, 15 people in universities and other educational entities. This hit people in primary and secondary schools, right? They got to the folks that are running your kindergartens. Also people in the government. 2 folks in government public administration got these mails. 1 person at a health provider and another person at an electricity and gas company, right? So they want all of our info, right? They don't care if you're a consumer. They don't care if you're a business. They don't care if you're a government. There is always something to steal from these different targets. And because they were localized, any of these folks could have been using these suppliers, right? So it was a social engineering lure that worked across the board. So how did we stop these attacks? Again, started at the client level. We extracted these properties. The client saw that these attacks were suspicious, not enough probability to block it at the client. We sent that information to cloud. Our cloud-based models returned malicious, and within milliseconds, it was blocked. All right. So, a few key points that I hope you take away. The attackers are clearly investing. 1.7 million new attacks in a single day. We have to invest to stop them, and so do you. We want to provide you the right tools and capabilities to do that. We know that the client security has to be effortless or it's not going to work. We want to have very low impact on the client, and we want to give you the tools that you need to administer those clients and respond to breaches when they do occur. We also want to provide you not just connected solutions, but also disconnected options too. Again, come talk to me if you have those scenarios, because I want to learn more about that. And most important, I hope you see that the M in machine learning doesn't stand for magic, okay? It's real, and it's absolutely critical to protect customers against the threats that we see today. All right. Thank you so much for showing up so early in the morning, and I hope this was valuable to you. Thanks.
This is TechDays.